Hello everyone. In this video, we'll understand about predicates and quantifiers. First one, predicates. A predicate is a statement containing one or more variables. If values are assigned to all the variables in a predicate, the resulting statement is a proposition. For example, if we say x greater than 5, here x is the variable and 5 is some value, right? So we can't say this is a proposition because we don't know the value of x. Depending on the value only, we can say whether we have a truth value as true or truth value as false, etc. So at this stage, since x is unknown, it is considered to be a predicate. Now, if I assign the value of x as 6, then 6 greater than 5 is definitely a proposition and truth value of that proposition is true. So let us consider the following statements involving variables such as x is greater than 4, x minus y equal to 7, x plus y equal to z. In the first statement, there is only one variable. In the second statement, there are two variables, x and y. In third statement, there are three variables, x, y, and z. All these are considered to be predicates. So these statements are neither true nor false since the values of the variables are not being specified. The statement x is greater than 4 has two parts. One is the first part, which is x, which is considered to be the variable. And the second part is the predicate, which specifies greater than 4. So we can denote this statement by p of x, where p denotes the predicate and x is the variable. So once a value has been assigned to the variable x, the statement p of x becomes a proposition, and that time it will have a truth value. If there is only one variable like in this p of x, which is x is greater than 4, then it is called unary predicate. The statement x minus y equal to 7 is called binary predicate because it has got two variables and is denoted by p of x comma y. So a predicate can have n variables also, like a p of x1, x2, and so on up to xn. That is called as n-ary predicate or n-place predicate. Some examples. Let p of x denotes the statement x greater than 3. What are the truth values of p of 4 and p of 2? So wherever x is there, we are going to replace it with 4 in the first one. And wherever x is there, we are going to replace it with 2 in the second one. So p of 4 becomes 4 greater than 3 and its truth value is of course true only. Whereas 2 greater than 3 is also a proposition, but its truth value is false. Another example, let p of x denotes the statement the word x contains the letter A, some word which contains letter A. Then we have to find out what are the truth values of p of orange, p of lemon, p of true, p of false. So here p of x is word x contains the letter A. Then the truth value of p of orange is true because it has got a letter A in this. Whereas truth value of p of lemon is false because it doesn't have the letter A. Truth value of true is false because it doesn't have the letter A. Whereas truth value of p of false is T is true, which is because it has got letter A in it. Third example, let q of x comma y denotes x is the capital of y. Now we have to find out what are the truth values of q of New Delhi comma India, q of New York comma New York, q of Bangalore comma Karnataka. So the q of x comma y is defined as x is the capital of y. So therefore the truth value of q of New Delhi comma India is true because New Delhi is the capital of India. Similarly, truth value of q of New York comma New York is false since capital of New York is Albany. Truth value of q of Bangalore comma Karnataka is true because capital of Karnataka is Bangalore. Next comes quantifiers. The expressions for all and there exists are called quantifiers. The process of applying quantifier to a variable is called quantification of variables. There are two types of quantifiers. First one is universal quantifier. Second one is existential quantifier. Then we will understand what do we mean by domain of discourse. Many mathematical statements assert that a property is true for all values of a variable in a particular domain. Maybe set of integers, set of real numbers, set of rational numbers, like that. That domain is called the domain of discourse, or it is also called as universe, or it is called as universe of discourse, or simply it can be called as domain only. Now comes universal quantifier or quantification. The universal quantification of P of x for a particular domain is the proposition that asserts that P of x is true for all values of x in this domain. That is, the domain specifies the possible values of the variable x. The domain must always be specified when an universal quantifier is used. The notation, this is for all, we read it as for all x p of x denotes the universal quantification of p of x. Here, the symbol v cross is called the universal quantifier. We read this v cross x p of x as for all x p of x, or we can also read it as for every x p of x. Some questions. Let p of x be the statement x less than 4. What is the truth value of the quantification for all x p of x, where the domain consists of all positive integers? So just finding one counterexample is enough to make for all p of x, x p of x false. Let us consider x as 5, then p of x becomes 5 less than 4, and that is false since p of 5 is false. X is equal to 5 is one such counterexample for the statement for all x p of x to be false, right? Hence, the truth value of p of x is false for the given domain. I mean, it doesn't satisfy to all positive integers. Let q of x be the statement x plus 1 greater than 2x. If the domain consists of all integers, what is the truth value of for all x q of x? Now, let us consider x is equal to 1. Then what happens? It becomes q of 1. Q of 1 will be 1 plus 1 greater than 2 into 1. It works out to 2 greater than 2, which is of course false. Hence, the truth value of for all x q of x is false for the given domain. Third example, if r of x is the statement which states x square greater than or equal to 0, s of x is the statement x square greater than or equal to x, and t of x is the statement x square less than 0, determine the truth values of for all x r of x, for all x s of x, for all x t of x, if the domain of each variable consists of all integers. So all integers means it can be negative or positive. So you substitute anything, definitely that even if I put a negative number here, since it is getting squared, it will become positive, and positive number will be definitely greater than 0. If I put x as 0 also, then it is actually equal to 0. So for all x, r of x will be true for if the statement is this. Now comes the second one. So if I put a negative number, it will become positive, and that number which do not have any sign will be equal to that number. So it can be, I mean, all the positive integers satisfies this s of x. That means for all x, s of x is true. Now, for the third statement, let us consider x as 1, then t of 1 will become 1 square less than 0, which is false. Hence, the truth value of for all x, t of x is false. Now, let us understand how do we express quantifications in English. Let p of x is defined as x spends more than 5 hours every day in class. Domain of x, which is consisting of all students. Now we need to express for all x p of x in English. For all x p of x means for all x p of x, or it can be said as for every x p of x, or for each x p of x, or for any x p of x. So we need to choose which will be the apt words for this, for us to express it in English. So step 1, for every x in the domain of all students, x spends more than 5 hours every day in class. Then we can further modify this as, without bringing this x and all, and domain and all, Every student spends more than 5 hours every day, every weekday in a class. Next one. What does the statement for all x p of x means if p of x is perfect and the domain consists of people in your locality? So step one, for every x in the domain of people in your locality, x is perfect. Then we can modify that as all people in your locality are perfect, or every person in your locality is perfect. Like that we can write it in English. Existential quantification. Existential quantification of p of x is the proposition there exists an element x in the domain such that p of x, denoted by the symbol inverted capital E. So there exists, we call it, there exists x p of x. Here, there exists is called the existential quantifier. Yet, domain must always be specified when a statement there exists x p of x is used. The other ways to say there exists p of x are there is an x such that p of x, or there is at least one x such that p of x, or for some x p of x. Now some questions. What is the truth value of there exists x p of x, where p of x is the statement x square greater than 10 and the universe of discourse consists of positive integers not exceeding 4. So if we consider x as 4, it becomes 16 greater than 10. So it is true. And at least one number satisfied. So we can say that the truth value of there exists x p of x is true because it satisfies for 4. Second question. Let q of x be the statement x plus 1 greater than 2x. If the domain consists of all integers, what is the truth value of there exists x q of x? Let us put x as 0. Then you will get q of 0 will be 0 plus 1 greater than 2 into 0, which is true. So at least we got one number, hence the truth value, which satisfies within that all integers domain. Hence the truth value of there exists x q of x is true. Third example, determine the truth value of each of the following statements if the domain consists of all real numbers. First one, there exists x such that x cube is equal to negative 1. Second question, there exists x such that x square lesser than x square. In the first case, let x be minus 1. What will happen then? Minus 1 the cube is equal to minus 1. So it is true for minus 1. Hence, the truth value of there exists x p of x is true because it satisfies at least one element. Let q of x be x power 4 less than x power 2. Let us substitute x for 1 by 2. Then what will happen? You will have q of 1 by 2 will be 1 by 16 because 1 by 2 to the power of 4 is 1 by 16. Lesser than 1 by 4 is true. Hence, the truth value of there exists x q of x is true. Now, some logical equivalences are involved, are there involving predicates and quantifiers, which is helpful for us to especially when we want to convert it into English sentences, it will be helpful for us. This is helpful in replacing one expression with an equivalent expression. There exists x p of x and q of x is equivalent to, sorry, I read it wrongly. For all x p of x and q of x is equivalent to for all x p of x and for all x q of x. That is one logical equivalence. The second one is there exists x p of x or q of x is equivalent to there exists x p of x or there exists x q of x. Then we have De Morgan's laws for quantifiers, which states as for all x p of x is equivalent to there exists x not of p of x. Similarly, not of there exists x p of x is, I think I didn't read this not. Not of all for all, sorry, not of for all x p of x is equivalent to there exists x not of p of x. That is one De Morgan's law. Second one, not of there exists x p of x is equivalent to for all x not of p of x. So let us do some examples in negation. What is the negation of the statement all dogs bark for all dogs, D barks. The negation of the above will be as follows. Not all dogs bark, or there exists some dog which do not bark, which is not, you can put it outside. For all dogs, D barks is equivalent to there exists dog D, not D barks. Second example, most cars are inexpensive. Solution for that is proceeded like this. The above is rewritten as there exists cars C is inexpensive. The negation of this will be not of there exists car C is inexpensive. So we can use that what do you call De Morgan's law for that. It can be rewritten as for all cars C, not of C is inexpensive, or that is for all cars C is not expensive, or we can simply write it as not all cars are inexpensive. So that is the end of predicates and quantifiers. In case if you find the contents of this video to be useful to you, I request you to please like it, share it with your friends, and also subscribe to my channel. Thank you.